For one of the last of these stats lessons, we're finally going to talk about regression. So, regression is an extremely useful analysis. When we talked about correlation, we learned that it can tell us about relationships between two variables, but it doesn't tell us how that relationship might change over time. And it also doesn't tell us how a third or fourth variable may affect both our x and our y. So, when we refer to x and y, what we're referring to is our independent and dependent variables. Our independent variables, usually labeled x, are our explanatory and our treatment variables. There can be one, there can be more per model, and these are usually known as the cause. Our dependent variables, usually labeled y, are the outcome or response variables. You can only have one of these per model, and this is known as the effect. So a couple parameters for regression. Here we have alpha and beta again. But here, alpha is our y-intercept, or the value of y when x is 0, and beta is the slope of our regression line. And we want to find the values of alpha and beta such that we minimize the sum of our squared regression errors. So, regression error. We can see here that we have a graph of quiz grades graphed against time spent studying. And it looks like a pretty strongly positive correlation here, right? But some of these points, actually most of these points, don't fall exactly on a regression line. And that's because when we fit a regression model, what we're doing is finding a best fit line that minimizes the squared errors or the squared differences of the distance from those points to the line. As an example, let's use education or years of education and income. So we want to find alpha and beta such that we minimize the sum of squared errors. So for beta, we're going to take the covariance of x and y over the variance of x, which would be 38,500 over 10, and we come up with $3,850. For alpha, we're going to take the average of y minus beta times the average of x, which would be 43,000 minus 3850 times 14, and that gives us negative 10,900. To interpret this value, when years of education is equal to 0, income is predicted by our model to be negative $10,900. To interpret beta, one additional year of education is associated with a 3,800 increase in income. So, we can use regression to make predictions. In the table below, you can see that we have the years of education and we have our income, y, but in the rightmost column, we have the predicted income based on our regression model. Now, notice that the predicted income didn't exactly match what the actual income for each of those data points was. And this is where the question, how good is our model, comes in. And we can compute error. So we want to compute mean squared error for our model. Now our mean squared error would be $233,100,000 divided by 2. Our degrees of freedom is 2 because we're estimating two parameters, alpha and beta. And our mean squared error would be about $116,550,000, which is a lot and doesn't really tell us a whole lot relative to the actual data that we have. So we take the square root of our mean squared error, and we get about $10,796. What you want with a regression model is a smaller mean squared error because it means that you have a better fitting model. One of the other ways to evaluate the fit of a regression model is called R-squared. And what R-squared does is tell us the percent of variation in y that is explained by our model. And this is the formula to compute the R-squared below. So if we wanted to compute our R-squared for our education and income example, we would do the following. Now, you won't have to do all of this by hand, and the formulas below are just an example, but our R-squared for our education and income regression model would be about 0.72 if we rounded, meaning that about 72% of the variation in income can be explained by number of years of education, according to this model. So, what we'd also like to find in a regression is the standard error of beta, or beta hat, which is our predicted beta values. The standard error of our predicted beta represents two quantities: the extent to which x explains y and the degree to which there's variation in x. So, for example, the standard error of our predicted beta would be about $1,707 in our income and education example. And finally, if we want to find out if this difference in income is actually significant, based on years of education, we can use a t-test and find a t-value. And then using our t-table, which I'm not going to show here, but our t-critical value will be 3.182. Now, if we compare this to our calculated t-value above of 2.23, our calculated t is less than our t-critical, which means that there's not sufficient evidence in our data to conclude that the difference of $3,850 in income is different from 0, meaning that even though we predict a difference in $3,850 based on years of education, this difference is not statistically significant based on years of education. Finally, there's some assumptions that we need to keep in mind when we're talking about regression. So, data used to fit these models are assumed to be representative of the population. So, our sample data need to be representative. We also assume that the true underlying relationship between x and y is linear in a linear regression. We won't really get into other types of regression in this video series quite yet. The variance, finally, the variance of errors is constant in our x, our independent variable.